All right, let's dive into a world where mathematicians try to predict the unpredictable using tools that power a multi-trillion-dollar global market. And believe it or not, it all kicks off with a pretty simple question.
I mean, really think about that for a second. What's a stock going to be worth next month? Or a currency next year? This isn't just about throwing darts at a board. It's a massive puzzle that the world of finance tackles every single day. And the key to even starting to solve it lies in a very specific type of contract.
And that contract is what we call a financial option. Now, the magic words here, the ones that make this whole thing work, are the right but not the obligation. So imagine you think a stock that's at $100 today is about to go to the moon. You could buy an option that gives you the right to purchase it for that same $100 anytime in the next month. If the stock soars to $150, you cash in your right, you buy cheap, and you've made a great bet. But if it tanks, well, you just let your option expire. You're only out the small fee you paid for it. It's like a ticket to a potential future. And this ticket comes in two main flavors.
A call option is your bet that a price is going to climb. It gives you the right to buy at a set price. A put option is the opposite. It's your bet that the price is going to fall. It gives you the right to sell. Simple enough, right? But here's the real billion-dollar question. What's the fair price to pay for one of these bets today?
So how did mathematicians first even try to solve this? Well, they started with something that's actually beautifully simple. It's a model that basically works like a choose-your-own-adventure story, but for stock prices.
You see, the genius of this model is its simplicity. It just ignores all the messy, chaotic noise of the real market for a second and makes one bold, simple assumption. In the very next moment, a stock's price can only do one of two things. It can go up or it can go down. That's it.
Here's what that looks like in its most basic form. You start today with one stock price. Then, in the next time step, let's say tomorrow, the world just splits in two. The price either jumps up to one very specific value or it drops down to another. It's a simple binary choice.
Okay, so one step is pretty straightforward. But what happens when you start chaining these simple choices together? You go from one day to the next over months. Each up or down fork in the road creates a new branch. And pretty soon, you have this massive, sprawling tree of possible price paths, a whole web of potential futures, all grown from that one simple rule. This is great for thinking in steps, but what happens when time isn't a step? What happens when it's a continuous flow?
And here's where that simple, elegant model starts to hit a wall. Because if you shrink those time steps, you go from days to seconds to milliseconds, those neat, clean branches just blur together. The price path stops looking like a series of clean jumps and starts to look like a continuous random jiggle. Scientists have a name for this: Brownian motion. You know, like the chaotic, unpredictable dance of a dust speck in a sunbeam. And to model that, well, for that, you need a whole new kind of math.
This new kind of math led to one of the most famous and, frankly, most powerful ideas in the entire history of finance. The Black-Scholes-Merton model was this revolutionary formula that could finally, for the first time, tame that randomness and put a real price on options in a world of constant, unpredictable change.
Their big breakthrough was using a field of math called stochastic calculus. Now, if you remember regular calculus from school, that's all about smooth, predictable change. Stochastic calculus, pioneered by the brilliant Kiyoshi Ito, is calculus for a messy, random world. It's not designed to model the smooth arc of a thrown baseball, it's designed to model the chaotic dance of a stock price.
This work was so incredibly groundbreaking that in 1997 it won the Nobel Prize. And this wasn't some idea that just stayed in academic journals, no way. This formula became the engine of a global derivatives market that's worth trillions of dollars. It literally changed the way Wall Street works.
Now, the formula itself is famously complex. But if you peek under the hood and look at the ingredients, they're actually pretty intuitive. You just need the stock's price right now, the option's target price, how much time is left on the clock, how jumpy or volatile the stock is, and the basic interest rate you could get risk-free. With those 5 pieces of info, you can price the future. Or can you?
But here's the thing about science. It never stands still. Even Nobel Prize-winning models have their limits. And some recent research is asking a really radical question.
What if the entire field has been looking at this problem from the completely wrong angle for the last 50 years?
What if there's a better, maybe even a more direct way to think about this whole problem? This is where a really fascinating mathematical trick called convex duality comes into play. It's all about finding a dual problem, a different problem that's way simpler to solve but gives you the exact same answer. So the classic approach, the Black-Scholes way, tries to model the incredibly complex movements of the stock price itself. This new approach, it flips that totally on its head. It suggests that instead, we should be modeling the option's sensitivity to those price changes. It's like trying to understand a statue by analyzing its shadow. The shadow might look a lot simpler, but it can still tell you everything you need to know about the statue's actual shape.
And this brand new perspective gives birth to something called the logistic model. It completely sidesteps the very difficult task of modeling the stock price. Instead, it directly models that sensitivity, which traders call delta. It goes right for what a trader really wants to know. Hey, if the stock moves $1, how much does my options value change? But this newfound elegance leads to a really fascinating trade-off.
So which one is better? The old, reliable workhorse, or this new, elegant challenger? Well, the answer, as you might guess, isn't so simple. It comes down to a classic battle: mathematical simplicity versus real-world complexity.
Okay, you don't need to be a mathematician to see the difference here. The new logistic model's formula is, well, it's just cleaner. It's more elegant. To a mathematician, it's theoretically more beautiful. But as we're about to find out, beauty on paper doesn't always win the race.
And here's the catch. When you actually sit a computer down and ask it to run the numbers, the classic model is faster. That simpler, more elegant new formula is actually harder for a computer to crunch. So mathematical elegance is one thing, but raw computational speed is a whole other beast.
And this right here, this reveals the core tension that's always beating at the heart of financial engineering. The search is always on for the Holy Grail, a model that is theoretically elegant, perfectly accurate in practice, and just lightning fast to compute. And that search, well, it's never really finished.
Which leaves us with a final, provocative thought to chew on. In this high-stakes quest to put a price on the future, what actually matters more? The mathematical elegance that gives us a deeper understanding, or the raw, brute force speed that wins in a market where every single microsecond counts? The answer is still being written. Thanks for digging into this with us.